Let's do a little bit more complicated example in much the same vein. We want to figure out where does this power series converge. And we're going to attack it in the same way. We're going to use the ratio test on the terms here. So here's going to be our AN. We're going to use the ratio test on those terms to figure out our rho. And then we'll have to check the endpoint separately. This all should be, once we do enough of these, this is going to feel very standard. Okay, AN plus 1 divided by AN, absolute value of that, is going to be, okay, everywhere we see an n, we replace with n plus 1. So minus 1 to the n plus 1, x minus 5 to the n plus 1, divided by 4 to the n plus 1 times n plus 1. All of that divided by minus 1 to the n, x minus 5 to the n, divided by 4 to the n times n. Let's rearrange this as before, group common things together. So minus 1 to the n plus 1 divided by minus 1 to the n. X minus 5 to the n plus 1 divided by x minus 5 to the n. This 4 to the n swings upstairs. 4 to the n divided by 4 to the n plus 1. And this n swings upstairs, n plus 1 downstairs. Okay, so what is canceling here? 4 to the n divided by 4 to the n plus 1. That just is 1/4. X minus 5 to the n plus 1 divided by x minus 5 to the n. That cancels down to x minus 5. Minus 1 to the n plus 1 divided by minus 1 to the n is just minus 1. Although we'll take an absolute value of that to get rid of that. And so after these simplifications, absolute value of minus 1 is 1. So it's 1/4 times n divided by n plus 1. Those are both positive things, so I can move them outside the absolute value bars. Times x minus 5, and we need absolute value bars there. Okay, so we've done the ratio of a sub n plus 1 divided by a sub n. Let's take the limit as n goes to infinity here so we can apply the ratio test. So rho is the limit as n goes to infinity of 1/4 times n over n plus 1 times absolute value of x minus 5. The 1/4 and the absolute value x minus 5, they're constants with respect to n. So let's move them outside of our limit. Oops, what's left inside our limit? N over n plus 1. And this limit, as n goes to infinity, that goes to 1. And so 1/4 times absolute value x minus 5 times 1. Excuse me. So rho is just 1/4 times the absolute value of x minus 5. Okay, so we know from our test, let's compare this to 1. And so rearranging this, we get x minus 5, absolute value of this to be less than 4. And so we know if this happens, then we get converge. And if absolute value x minus 5 is strictly larger than 4, then we get diverge. Now I'll put in here absolutely converge. And so then the leftover thing that we have to do is figure out at the endpoints. So let's go to a new slide to look at the endpoint calculations here. Let's draw a picture. So our center is at 5. We can see that here. We can see that up here. The center of our power series is at x is equal to 5. And our radius of convergence is 4. So x minus 5 is equal to 4. That's at 1 and 9. So what's going on here? So it absolutely converges on the interval, the open interval from 1 to 9. It diverges if x is bigger than 9. It diverges as x is less than 1. And so our last thing we have to do is look at the endpoints, look to see what's happening if x is equal to 1 and x is equal to 9. Okay, so when x is equal to 1, let's plop 1 in here and see what happens. So sum from n from 1 to infinity minus 1 to the n over 4 to the n times n. And then we have 1 minus 5 to the n. Okay, so let's manipulate this a little bit. This is going to simplify way down. Minus 1 to the n. That's minus 4 to the n divided by 4 to the n times n. And minus 4 to the n is just, that's just going to be minus 1 to the n times minus 1 to the n times 4 to the n over 4 to the n times n. Cancel, cancel. That's minus 1 to the 2n. That's going to always be 1. And so we are just left with 1 over n, the sum of 1 over n, and this diverges. This is the harmonic series that we've seen before. It's a p series. P is equal to 1, so this is exactly, so it diverges right here. Okay, so it diverges at x is equal to 1. Okay, what's our other case? We have to think about what's happening when x is equal to 9. So plop 9 into our series. Minus 1 to the n over 4 to the n times n. 9 minus 5 to the n. So cancel, cancel. And so what are we left with? We are left with the sum of minus 1 to the n over n. And so this is the alternating harmonic series. This is going to converge by the alternating series test. Okay, so what happens now? So to conclude, where does our series converge? The sum from n from 1 to infinity of minus 1 to the n times x minus 5 to the n divided by 4 to the n times n. It converges on the interval from 1 to 9, and it's open at x is equal to 1 because it diverges there, but it does converge when x is equal to 9. So here we see a case in which it converges, our power series converges at exactly one of the endpoints. So in the previous video, we saw an example where it diverges at both of the endpoints. Here we have one where it converges at exactly one of the endpoints and diverges at the other. It's also possible that our power series could converge at both of the endpoints. So once again, this is a very standard example for how to tackle these issues of convergence. We're almost always going to do these with the ratio test. So carry out the ratio test here. You have something left in terms of x here. Calculate out rho. This tells you most of what's going on. And then the last thing we have to do is use other tests, which could vary from problem to problem, to see how we're going to take care of the endpoints. So very typical problem.